So we're going to look at formal charge as a way to figure out the best structure where you potentially have different atoms that you can decide or choose to form a double bond or triple bond with. So formal charge, we can call it FC or formal charge. Formal charge is simply you're just going to look at the number of valence electrons. Oh, valence. Whoa, we got this. That you have, and this is going to be calculated for each atom. So number of valence electrons for an atom. This is how many electrons this atom came to a bond with. And then you're going to look at the structure that you created, and you're going to say, okay, well, how many electrons are unshared? So number of unshared electrons. So those are going to be electrons associated with lone pairs. So this again, this is it's going to be a lone pair electrons, and then you're going to add to that 1/2 of the number of electrons in a bonding pair. And we do 1/2 because in calculating formal charge, we cannot double count electrons. And we'll give you an example of this here in a sec. If we want to define formal charge, what formal charge is, we call this, it's the number of electrons formally assigned to an atom in a molecular structure. Now, the reason we do that is we already have learned that there are some atoms that are more electronegative than others, and so stability is going to lie in the best structure will be the most stable structure. And so we have a couple rules of formal charges to say, okay, well, if we're going to put more electrons on one atom, which atom should that be? And so we use formal charges as a way to construct those rules. Okay. So for example, let's just do a structure that we've already done. So let's say we have, let's do let's do SO3, because all these have the same structure. We're going to do SO3. That's a good one. Okay, so SO3. We'll just choose one of the three structures. They're all the same here. If we're going to calculate the formal charge, we'll do that in purple. Let's first do it for, let's make sure the right number of electrons here. Okay, so let's go and calculate the formal charge for, we have three types of atoms. We have an oxygen that's double bonded. We have an oxygen that's single bonded. And we have a sulfur that has, that oxygen, that has 4 bonds. Okay, so the formal charge for the oxygen that's double bonded, number of valence electrons, it's always going to be 6 for oxygen, so that doesn't change. And we're going to subtract from that the number of unshared electrons, that's going to be 2 and 4 from the non-bonding, so that's 4. Plus, we have number of electrons in bonding pairs, that's going to be 4 as well, 2 from each bond. So it's going to be 1/2 times 4. So we can see that this is going to be 6 minus 4 plus 2 is 6 is equal to 0. So we would assign this oxygen to have a formal charge of 0. Okay. If we look at the oxygen with a single bond, 6 is still going to be here. We now look at how many electrons are unshared. It goes from, we have 6, 2, 4, 6 of the lone pairs. That's going to be 6 plus 1/2. Now we only have 2 electrons that are in a bond, and so it's going to be 6 minus 7. And so we get a -1 charge here. So these 2 oxygens are -1. Now it turns out whenever oxygen has a double bond, it has a formal charge of 0. Whenever oxygen has a single bond, it's got a formal charge of -1. So you start memorizing some of these just by doing this often or making this calculation. Now, sulfur also has 6 valence electrons, and it has 0 electrons unshared, and all of its electrons are shared. So that's 1/2 times 8. So we have 2, 4, 6, 8. So that's 6 minus 4 is equal to plus 2. So we have a plus 2 for sulfur. Okay, and so that's how you would assign formal charge. And so if we have multiple structures and we're trying to determine what is the best structure, then we have 2 rules, and we're going to first state the rules, and we're going to use them in an example. So the first rule is that we would like to have the most formal charges of 0. So formal charges equaling 0 is so this represents best structure. So that is to say that the structure that has most atoms with a formal charge equal to 0 is the best structure. Now, sometimes that is impossible. Sometimes we would have one structure or multiple structures that both have like the same number of atoms with a formal charge of 0. In that case, a kind of an inset, the second rule is based on if you have multiple structures and they all have the same number of formal charge of 0, maybe that's 1, maybe that's 2, then we're going to say which structure puts the negative formal charge on most electronegative atom is the best structure. And we're going to do an example of this next. So you can see if we can write structure, right? Okay, so we're going to do an example. But basically, most formal charge is 0. That's the best structure. If we can't have all formal charges of 0, that negative formal charge is going to be there then. We want that on the most electronegative atom, so most often that's going to be oxygen for the examples that we're going to see. So here's the example, N2O. So if we do this, I'm going to walk through it together. This is a really good molecule to practice on. So we have nitrogen, oxygen, and total. So we've got number of valence electrons. Nitrogen has 5. We have 2 of those. That's 10 electrons. Oxygen's got 6 electrons times 1, so that's 6 electrons. So 16 electrons total. If we look here, so this is actually where it kind of matters. Nitrogen needs 3 bonds. Oxygen needs 2. So nitrogen is going to be our central atom. And so I'm going to put a nitrogen here, and then a nitrogen on one side, and an oxygen on the other, giving the nitrogen the central atom. Okay, so that's our initial structure, and then I'm going to give an octet to the 2 outer atoms, and I'm going to count up the number of electrons. And so I count up the number of electrons. We got 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 electrons. And that's what we need. So I can't add any more electrons to my structure, but we can see that the nitrogen needs 2 more sets of electrons, 2 more bonds to get a total of 8. Right now it only has 4 valence electrons. And so there are actually 3 ways to do this. So the first way is to give both sets of lone pairs from the nitrogen. And if we do that, we would get this structure: triple bond, nitrogen, single bond, oxygen. And then if we instead do both lone pairs from the oxygen, we would get that with this structure: triple bond, oxygen, single bond, nitrogen. And the last one is we could do one from each. So we could have one from the nitrogen, 1 from the oxygen, and that would give us 2 double bonds between the nitrogen and a double bond between the oxygen. Okay. Now these structures are different. These are all these are unlike. We're not going to put double-sided arrows here because these are fundamentally different structures. We have different bonds, numbers of bonds to different atoms, and so because of that, we need to figure out which is the best structure, which is the worst structure, and which is the meh structure, the one that's in between. So to do that, we're going to need to calculate a formal charge for each atom. So for each nitrogen and oxygen in each of the structures. Okay, so we're going to do that, and we'll be able to. I'll make a little chart here, so we can see that we have a nitrogen single bond with lone pairs. We have a nitrogen double bond with 2 lone pairs. We have a nitrogen triple bond with a lone pair. Okay, that's one key. We also have a nitrogen with 4 bonds. And we have a nitrogen with these are the same 4 bonds. Okay, so let's just go ahead and do all the nitrogens first, and then we'll assign them. I think it's just nice to have them all down below. So if we look at the nitrogen with the triple bond, in all cases, nitrogen starts off with 5 electrons, and then we're going to subtract from that. In this case, the nitrogen has 6 electrons that are not in bonding, plus 1/2 of 2. That's equal to 7. 7 minus 5 is -2. -2. That's showing you that those electrons are, or that nitrogen is electron rich. So we see that right here. So this is -2. I think that's the only one. Yeah. Nitrogen double bond. We're going to have still 5 electrons. I shouldn't put the electrons there, sorry. So 5, just 5, minus, now in this case we have 4 unshared plus 1/2 of 4. So you'll see that this goes down by 1. So we have 4 plus 1 is 5. 4 plus 2 is 6 minus 5 minus 6 is -1. So by removing a lone pair or adding a bond, it goes down by 1. Okay, you'll see a trend here, and that's where we're kind of writing these out like this. So we go and we see the double bonds here. That's -1. I think that's the only place where I see that. Okay, now the triple bond with a lone pair, still 5 minus, in this case we have 2 plus 1/2 of 6. And if you see these trends, we can see that this is now 0. So we have 2 plus 3 is 5, minus 5 is 0. So you can see as we add bonds, the formal charge goes to 0. And where the formal charge of 0 is where we predict nitrogen wants to make 3 bonds. When it makes 3 bonds, a formal charge is 0. So 3 bonds are going to be a formal charge of 0 here. And I think that's it. And then for formal charge of when you make 4 bonds, if we're following this pattern, if I make 4, I should have a +1, but let's just make sure we have that. So that's 0, no lone pairs, plus 1/2 of 8. That's going to be 5 minus 4, plus 1. So we see a +1 here, we see a +1 here, and we see a +1 here. That takes care of all the nitrogens. Now if we go look at the oxygens, we're going to have the same thing, single bond oxygen. We're going to have a double bond oxygen. And we're going to have a triple bond oxygen. Because oxygen is not the central atom, we will not have oxygen with 4 bonds. Okay, we'll see a similar type of trend. We start off with 6 electrons for oxygen. The single bond, we have 6 plus 1/2 of 2. So in this case, because we have 1 extra electron, this is going to be -1. So we can do that here, -1. That's the only one. For a double bond, we would expect it to be 0. But let's just make sure it is 1/2. That's not 6, sorry, it's 4. 1/2 of 4. So that's 6 minus 6. That's going to give us 0. And we would expect this to continue to go up to a +1 charge. So this is, now we have 2 plus 1/2 of 6. That's 5. 6 minus 5 is +1. So we should see this is 0. I forgot to put that. And this is +1. Okay. So again, I just want to show that as you increase the bonds for either nitrogen or oxygen, we go from negative, where the zero formal charge for both is the number of bonds that we would predict up in this table. So when oxygen makes 2 bonds or nitrogen makes 3, that's when we see the formal charge of 0. That's what we predict to be the most stable form. So just pointing that out. Okay. So now we look at these structures. Which structure has the most formal charges of 0? Well, the two that have the most formal charges of 0 is 1, and that's right here and right here. So off the bat, this middle structure is, we can say that this structure right here is the worst. You are the worst. Worst structure. Sorry about that. So now we need to go and compare the structures 1 and 2. Okay, so if you remember our rules, so now we have found 2 structures. They both have 1 atom of the formal charge of 0. So now I need to figure out the structure that has a negative formal charge on the most electronegative atom, which is going to be oxygen in this case. So this structure has the negative formal charge on nitrogen. This structure has a negative formal charge on oxygen, making this structure the best structure based on our rules. And this structure is our meh. It's not the worst. It's not the best. And so we would expect to see most of these N2O molecules looking like a nitrogen triple bond and a nitrogen oxygen single bond. So that's how we use formal charge to determine the formal charges and structures of atoms that have multiple kind of options. Like, just to show you, when we have right up here, when we kind of like choose your own adventure, which one can we do? When you have options, for whenever you have a different option, that's a different structure. If those structures aren't equivalent, you have to evaluate using formal charge. And so make sure you can do that. Make sure you can evaluate which is the best. And then we can establish, something about bond length and formal charge in that way. So there's different ways that we can kind of like ask those questions on exams. But at the end of the day, draw the structures, assign formal charges. Again, this was a lot of work to assign formal charges. I really just did this to show you the trends of how you would assign formal charges for resonance structures. But you're going to start memorizing oxygen with a double bond is a formal charge of 0. If it has 1 less bond, it's negative. 1 more bond is positive, and so on and so forth.